So we're very happy to have with us today Dr. Conrad Bock from the U.S. National Institute of Standards and Technology. He is with the engineering laboratory. He's a computer scientist there, and he's specializing in formal models for products and processes. And he's the laboratory's lead for system engineering standards, and also he co-chaired system modeling language revision task force at the Object Management Group, which you know is a formal body that discusses all these languages. He was the founding editor of the activity and action models in a unified modeling language, and later on the system modeling language at the Object Management Group, as well as a primary contributor to interaction modeling in the business process models and notation. So today he's going to talk to us about logical modeling for engineering, which is another word for ontologies. Right? Good morning.
Thank you. Logical modeling, actually I avoided the onto words here because they're the same thing, particularly kind of ontology for description logic. So that's what I was going to talk about today in the context of engineering. The overview is basically first just a brief comparison between modeling you're probably familiar with of the quantitative kind and the logical kind. And then we'll talk about the central concept in logical modeling, which is categories and the various aspects of it. We'll talk about building categories of categories, which relates directly to building domain-specific languages like engineering languages. Then we'll talk about the applying categories to relations, and also just one slide on processes, so you can have an idea how that works. And then summarize. So quantitative modeling, I think you guys are all familiar with. You use a fair amount of mathematics in particular. It's only there, it can do with equations. There might be simulations. They might involve stochastic elements. And the purpose really is to calculate numeric values, simulate them, or perhaps derive new formulas, numerical formulas. Whereas when you look at logical modeling, it's about categorizing things and the relations between them. So for example, you might say, well, this document is a requirement, falls in the category of requirements. This document is a design, falls in the category of designs. You want the design to meet the requirements as a relationship between them. So it's concerned with categorizing those things and also keeping the categories consistent. So do we know that the designs actually meet the requirements? And suppose they change, does the satisfaction relationships still they hold or not? Those are all questions that would be involved in logical modeling. So categories are basically the conditions, specify the conditions for which things must need to fall in them. Now, the important thing to remember is that categories aren't the same as the things that fall in them. They're just a set of conditions. So for example, we say that, say we have a category for things that float, and you have a condition, well, its density has to be greater than water, or less than water. Actually, that's reversed. It's been a long time since I did this. So these individual things down here are meant to be actual individual things, like that's the plastic bottle sitting under my kitchen at home. That's a ship with a certain serial number or registration number sitting in a certain dock. And these individual things meet those conditions, and so they're in that category. They're not the category of ships and so on. Those are actual individual things. And then there's other individual things that fall outside the category. But the category itself is not the same as that set. In set theory, each time you change the elements in a set, it's a new set. So categories are not the same as sets, even though you might talk about the set of things that fall into them. So following on that line, suppose we said we changed that definition to include, to be more specific. We want the things that float, but also that exist. The things with density is correct, but also that exist. Well, that'll change over time. Plastic bottles come and go. At a particular time, we might have this new plastic bottle, the duck and babies, and so on. These the ship, for example, right now might not actually float. There's a hole in it. So this is actually a different set from the one on the previous slide, but the category hasn't changed, except we changed the condition. This set of things that falls in the category will change over time, even though the category doesn't. And that's what makes it different from, say, a typical self-directed viewpoint. Another thing about categories is they don't imply, although in that last slide we added a condition that the thing actually exists, it doesn't imply existence. So, for example, we might have a category for Roman cities that has conditions that will be true for Roman cities, but Roman cities don't exist anymore. Cities exist that were Roman, but there's none now. And we might also, say, have a category with the conditions that describe marketable solar cars. Well, they don't exist now, but that doesn't stop us from making the conditions. And this applies, of course, to anything you do in product design, because the product could well not exist, usually doesn't exist in advance. But that doesn't stop us from making the category. And also, the category can describe things that don't exist, or you don't expect to exist, like perpetual motion machines. You can define the conditions of that very simply. You can't really find any instances of it, so that would include all the imaginary things. Or
is existence related to something you think about only, or also related to physical laws and things like that?
Well, what I meant by exist here was physically exist now.
So implementation.
Yeah.
So this is an instance that is being constructed, the real thing.
Right. And I'm also including things, you're allowed, the things that fall in the category can be anything you choose. In mathematics called the domain of discourse. It's just whatever you choose. So for example, if you want to consider categories of simulation events or things that are in your simulator, that's fine. That would be like in this middle case. They don't exist yet, but you're simulating them. So you can, the flexibility as to what you consider to be the things in your category or the domain of discourse is really up to you.
Does that imply material or immaterial things? Or
A
concept too?
Yeah, it could be. You could, for example, if you imagine your domain of discourse is religion and spirituality, you could imagine artifacts existing in that realm and make categories for them. It doesn't. The fact that you write the conditions doesn't imply anything about the physical existence of things. And they're just the conditions. And that's important because we know that sometimes you can make a product design for something that can't be built. I mean, maybe it turns out that it's impossible. And part of your analysis work is to figure out that it's impossible. So it's important that the category and conditions are separate from the things that might fall into it. The conditions that are on the category are not immutable. You can change them. We did that on the first slide. We added the existence. Here's a case. If you have an object, a thing that you think should fall in the category, but for some reason it's failing the conditions, you can do two things. You can modify these things so it meets the conditions. You can modify the conditions so it allows the thing. The conditions aren't inviolate. So, for example, if you have a category for cars, well, produced by that's essentially the design. You want your cars to meet these certain conditions. Well, maybe this factory produces one that doesn't meet those conditions. In that case, you're going to modify the car, or you're going to modify the factory, or you're going to do something so that that car either is recycled or remanufactured or somehow is changed in a way that it meets the condition. Or you could have another category that's just the category of things that come out of that factory, that are built in that factory. And then in that case, if you ever have something that is produced by that factory, but for some reason fails the conditions of the class, of the category, you have to change the category. So these are the difference between categories that are meant to specify what you want out of reality versus categories that are meant to reflect reality. So it can go either way. Another reason I went through this is that in the presentations of this to engineering folks, these were the common set of misconceptions about categories. They assumed that they had to exist or that they were immutable or something like that. These are usually the common set of things I find that are confusing for people that first approach this stuff. So all of that was using my informal terminology. I call them categories because I think that's what people normally call them. This is a terminology that's in various languages. So in the unified modeling language, UML, you will see them called classes. That's also the name in the web ontology language. In SysML, the systems modeling language, which is an extension of UML, they changed the name of classes to blocks. So they just felt that was better for their particular community. And then the things that fall into the categories in both UML and SysML are called instances. And the reason this is important to look at is that those concepts I showed you before are fairly easy to understand. I think anyone can understand without too much training. But then there's a matter of mapping them onto the many languages that you might have, the category languages that, and it can be very confusing because the category languages have all these different terminologies. And it's important to know the concept independent of those particular languages. So this is the notation you see in UML and SysML. This rectangular shape is what they use for classes. Or in SysML, they'll put this little tag on the top, which indicates that it's a particular kind of class called a block, which only has certain restrictions. And then the constraint of the condition is done with that little note shape you see on the side. Or SysML added additional notation where you see it, the constraints in a little compartment. And one thing I should point out is if you look at UML and SysML models as they're actually built, they usually use the singular. They'll say, thing that floats. They'll say car. That's pretty much uniform over a lot of the communities that use these languages. And I used to think that was a good idea, and after a long time of trying to help people with it, I decided it's a really bad idea. But usually what happens is you can get an engineer who will make a class or a block, they'll call it car, and they'll start to think of it as an actual instance of a car. And what that prevents them from doing is figuring out, well, what are the conditions to be a car? Do I want more general conditions or more specific conditions? And they stop thinking of it as a category. So there's really no law that says they can't be plural, but or have to be singular. But you will run into that a lot. And if I were doing it for the first time, I would use plural. So it's easier to indicate it's a category. These are the diagrams you see in UML and SysML. For some reason, UML doesn't have a class diagram. It doesn't package diagram for classes in it. SysML has something called a block definition diagram. There's blocks in it. So that was the basics of categories and then the notation. These next set of slides are basically about two kinds of conditions, to distinguish two special kinds of conditions, and also talk about later on the most common kind of condition that you see. The first one, those are called name conditions. They're conditions that just tell you when something is in the set, but they won't tell you when it's out. It sounds confusing at first, but for example, if you have this condition at the top that says any four-wheeled thing with certain other characteristics is a car. If something meets that condition, it's going to be a car. But if it doesn't meet that condition, that doesn't mean it's not a car. It could be that some cars, there's another sufficient condition that says, well, three-wheeled things with those categories, with those categories are also cars. So when you look at a purely sufficient condition like that, they won't interact. Each condition is sufficient separately. There might be three-wheeled cars, four-wheeled cars, and so on. And those might have a separate condition. And then there's the out conditions, which is a term I use for what we normally call the necessary conditions. These are ones that determine when something's out in the category, but they won't determine whether it's in it. So for example, I say cars or vehicles. Well, this will tell you when a condition is not, when something is not a car, because if it's not a vehicle, for example, you know it's not a car. However, it won't tell you that it is a car. Because if you know something's a vehicle, it doesn't necessarily need to be a car. It could be a truck. And again, the necessary conditions don't interact. But when you combine necessary and sufficient, because one's talking about what's in the set and one's talking about what's out of the set, they can conflict. So if I say a sufficient condition is that the car has three wheels and certain other characteristics, and then I have a necessary condition, an out condition that says that they're four-wheeled, then I have a conflict. But if you use each of them alone, you can't get a contradiction. This is important if you ever have the dubious opportunity of reading Defense Department requirements and things, because a lot of this is written in English. And the way to read those things is just to note that you have an in condition if you see the category at the end of the sentence. It'll be able to say, any four-wheeled thing with certain characteristics is a car. That's an in condition. Cars are vehicles when the category is at the beginning of the sentence. That's an out condition. That means it's necessary. But sometimes you'll see, accidentally, people read that first one, the four-wheeled thing over 750 kilograms, they'll read that as also being necessary. For example, that it must be that the car has four wheels. And those, I mean, it depends on how you parse English, but formally speaking, when you work it out, that's just a sufficient condition, not necessary.
There's been a famous Greek oracle that will take a sentence and depend on where you put the commas in the meaning, you know that.
Yeah, it's like this. Of course, I think what a lot of people read these sentences as being both in and out, necessary and sufficient. And these kinds of conditions, of course, can tell you exactly what's in the set and what's not in the set. So, for example, these mathematical set descriptors, they're meant to say that things that are less dense than water are in the category. I think again, I flipped my grade sign. Things that are more dense or the same density are out. So this tells you exactly what's in, exactly what's out. That's a necessary.
Well, it depends on what you mean by this. So you may be correct, but you never define what that means, greater or less, right?
Well, this is meant to be a numeric.
Yeah, I know, but
density is less than.
It could be defined that way.
Oh yeah. So this is actually.
No, that's the comment which is more serious. You know, sometimes when you go from words to mathematical expression, you have to explain it.
Right.
Well, that's not also done.
Yes, in fact, yeah. Sometimes, especially, there's a lot of text that will write a notation and then give some examples, but not actually tell you the meaning of the notation.
Right. So sometimes if I use not the inequality but this thing, right? This means preference.
Oh yeah, which is not
So
inequality.
if you use standard of what you call it stock quantitative, and then I use logical descriptors, I have to define them, otherwise
Right.
that can be a help.
Right. So I guess using the standard interpretation of it,
Yeah.
these mathematical set descriptors are both necessary and sufficient. So that's more about conditions you probably want to know. I wanted to go to probably the most common condition you're going to see, which is something that says that all the things in one category fall into another. So we say that cars are vehicles. It means anything falling in the car category will fall in the vehicle category. This is a necessary condition on car, but it's a sufficient condition on vehicles. But this is the typical thing that we see as the first kind of thing we see in most modeling. And so it's given a particular notation. This is kind of important because I think I give a separate talk on the software interpretation of this symbol, which is more as inheritance. But from a logical point of view, which UML can be used in a logical way, it's meant to mean the condition on the previous slide. And in UML and SysML it's called generalization, and in OWL it's called subclass. And it only means that any instance of car is an instance of vehicle. That's all it means. And often a lot is read into that, but that's the formal meaning of it.
And you have more than one, right? So I can talk about circuits, and then I have digital circuits, then I have analog circuits.
Right. You can make what we
Do
call
they interact?
Yeah.
Do they overlap?
Yes.
Yeah, you can make what's called taxonomies. That overlapping thing is one of the gotchas about it. So, for example, here we have multiple generalization. We have some conditions, say, on car, some general ones, and then we have specific things having to do with low emission, some conditions for recyclability, streamline. And then we combine these all into this category. And this, which is typically called taxonomy, from an engineering point of view, looks like design refinement, and then also design aspects and alternatives that are mixed together.
Do you have examples of where the two can be, I mean, if I have multiple generalizations, two can be confused. That's more for you, but I mean, suppose I do for I have circuits, then I have, or electrical, electrical matter, electronics, whatever you want to call them, that's the big block. And then I have two blocks, digital microelectronics, and then I have analog.
Right.
Now, a lot of people will tell you that many of the analog implementations are actually digital. How do I handle that?
So that's it.
And you people a lot of times cheat. It's analog, it's not analog, it's digital analog. Like the best example I know is neural networks, which are not really analog, they're digital. How do I handle that here? It depends. But
Well, it depends on how you define the conditions. You can define these conditions in a way that
So I need to give more conditions to make sure that I avoid this kind of confusion, correct? Or I have to,
Yeah, if you
or
really
do
want
I have to create another subcategory?
well, I think this, I'll get your question in a second. I'm just gonna, these are very gotchas that come about when people confuse, lay more meaning on this than simple subsets. So for example, the fact that I made these generalizations doesn't mean there aren't cars that don't fall into any of these really lousy cars. It also doesn't, that previous doesn't prevent from having, say, some cars that are recyclable and streamlined but not low emission, which would be these partially overlapping.
So they can overlap, and also as I go from the big category to the subcategories, they can be, cannot be exhaustive. There can be other things that I just did not put there.
Yeah, like a lot of folks, when they look at that previous one, they'll think that good cars, all cars that have low emissions, are streamlined and recyclable are good cars. That's not actually what that said. You can't say it in UML, but you have to add more stuff. So if you want to get rid of all these little gaps and things in here, there's other annotations you can put on the UML diagram to lock it down so that those aren't there. But just as it's read, if you didn't adopt any of the conventions, you get this kind of flexibility.
I had a question. Some languages, such as Java, they don't support multiple components. And you should find another way using software design patterns to go some way around it and use that functionality. But I have a question in a situation that, assuming using Java as a language, that you sort of have to have a class that's extending to other classes. Assume that, let's say good cars, okay. It's extending 70% recyclable in streamlined cars. And there are two other classes that would accept these good cars as a class, but one would take it as a 70% recyclable, the other one would take it as in streamlined cars. What is a way, or how you can deal with those situations?
Well, the first book to read on any of that stuff is the gamma patterns, which you probably know about. The main purpose of the gamma patterns book is to do the things that you might expect out of logical modeling. They don't say it this way. But when a person like me reads it, what I see is many ways of getting languages, mostly compiled languages, or languages that don't have all the capabilities of a logical language, what pattern, what way to use them to get there. In the particular case of this, I see a lot of folks use interfaces because you can say, well, I'm going to have, they make this into a particular class that support, and they make these interfaces. Then you can have cars that support one or all of these interfaces.
Yes.
This is a real difficult matter because the engineer, for toolmakers, because the engineer may be looking at it, is usually looking at logically. They actually, a lot of engineers, well, not necessarily have been trained in object orientation. And then it's the job of the toolmaker to figure out if they really feel they have to generate code. They have to keep track of what particular pattern they use to get there. And then if there's a problem that happened when the code is running, to reverse that and reflect it in the interface given to the engineer. It's really a hard problem. And a lot of toolmakers instead actually choose to make a logical modeling layer on top of whatever language they're using.
That's cleaner, I think.
Yeah, in the end, it's a lot easier it's a little slower, but it's a lot easier.
So if you try to force everything in Java, my suggestion is it won't work. That's why if it worked, it wouldn't go to the set of languages.
Yeah, it's a sticky problem getting between. I could give a whole talk in relationship to software, because it gets very confusing. Because they also have the word class. They also have some notions that are sort of related to generalization, like inheritance, but they're not quite the same. So if you're in a situation where you're talking to engineers and you have to transition that work into what they're saying into software, which is actually what the purpose of UML was in the first place. It starts out with, actually one of the early applications was describing electric motors. And they just had people who knew electric motors and nothing else, and they had to get to a relational database. That whole process is non-trivial. The purpose of this talk really is to establish this place at the logical end. And there is still a lot of work actually on how you integrate it in with software development. So yeah, there's all these little holes there. That's that diagram you little bit. So moving on to looking at this in terms of, again, in terms of product application. We know in the ideal world what we want is we want cars when they're built and maintained to be built and maintained according to the design. And we want the design to meet the requirements. And that ideal world is reflected in this kind of taxonomy. We say we're going to categorize the cars as that would meet requirements, certainly individual cars, rather than a class of actual cars. The cars that would meet these requirements, and then you would hope that cars that are built that meet this design would also meet these requirements. That all cars that are designed this way would meet these requirements. That's what we want. You want the cars as they're built and as they're maintained also to follow all the conditions that are specified in their design. This is the ideal world. Of course, the ideal world, that isn't what we live in. That diagram you saw, you would normally expect all these to be nicely nested sets, but they aren't. You get cars that are where the design conditions actually cause possibility of cars being built that don't meet the requirements, or cars that are not built as they're designed. Or even these other weird cases that might happen where you have a car that's built as required but not as designed. The purpose of analyzers and reasoners is to try as early as possible in the product development cycle to predict the possibility that there might be these cases. And that's really what the purpose of the reasoners is to do. So you can go ahead and enter into your model this. This is what you want. And then what your analyzers and reasoners do is tell you where you're wrong. They tell you, well, I had these conditions in the requirement, and it looks like some of them are actually not going to be met by the design, and so on. So this again indicates flexibility of the categories. The fact that you write this down doesn't mean that necessarily. So you find that out later with the reasons. So that was all about categories. Going to its, although this sometimes hurts the head, it's very useful to talk about categories of categories, especially if you want to make all of that stuff intelligible on the engineering side. So we had these various categories. We had requirement categories and design categories, which are categorizing actual things. These are the actual things, or the things that will be there in the future and so on. But then I want to say, well, actually, from the point of view of category, there's nothing different between one that has requirement conditions and one that has design conditions. The notion of category is to distinguish them. So in order to distinguish those, you say, okay, well, actually, we want them to be two different kinds of categories, at least, that we use in engineering. We have ones that specify requirement conditions and ones that specify design conditions. And then these
categories fall into those categories. And these real or
What's
imaginary.
exactly the distinction between design categories and requirement categories?
Well, so that depends on the definition of requirement. And for example, in one of the areas, one of the things that we published, we said, okay, well, a requirement is any condition about the environment of the artifact when it's being used. That's one definition. So for example, we expect for a lawnmower that when you use it, the grass gets shorter. The grass is outside of the artifact, and therefore it's a requirement. And under that model, anything that's a condition on the inside, for example, that is gas powered or that it has a
certain kind of way of sparking the gas. All of that would be part of the design. This is about the inside of the thing, and actually the operator doesn't really pay any attention.
This is not a bit confusing because when I teach the course, I split completely. I say anything you ask me that the system or anything that I have to do in the design, I call it the requirement. When it is expressed in its natural language, when I translate mathematics, I call it specification.
You can do that.
In which case, you know, I'm drawing a line between these vague things that you start in the beginning versus when I know precisely what you mean. Like, anytime you operate a lawnmower at the setting 3, it has to cut the grass by 2 inches. When I get to that point, I call it specification.
Okay, well, that would be fine. But the example I just gave you was just one definition we used for these
What is
categories.
the standard? Is there a standard in this phraseology?
Not that I'm aware of.
Okay. Otherwise, I'd be worried because they get, I have seen them used all over.
Yeah, well, you know what you could do. Underneath requirement categories, you could develop an entire taxonomy of the various ways that people define requirements. In your case, you have a condition saying that it must be textual, for example. And that's actually talking about how these conditions of these categories are specified. So yeah, there's a whole, there would
Because
be
the way I'm
entire
thinking
research
is-
field behind it.
Yeah,
How do
and
you
the way I'm
define it?
thinking is once you go from requirements and you make your blocks, you annotate your blocks, at that point, before you do design exploration, you have to quantify everything, meaning you have to translate it into some numerical or logical thing that can be searched and argued about.
Right.
Otherwise, you cannot do design space exploration.
Right. And you could actually, if those conditions are fairly easy to test for and they're fairly clear, if you made those the conditions, those categories, then of course you could, the reasoners could help you detect when you said when the design, but you didn't make it because some things are still informally specified. So once you do this, once you decide, well, I'm going to have categories in my categories, you have the opportunity then to shift over to a language that's more closer to the engineer. The engineer's not thinking, oh, this is a requirements category. They're just thinking the requirements. They're not thinking, oh, this is a design category. And they're not thinking about categories of categories. Just call them that, and this is kind of what SysML does. It just says, well, I'm going to start talking using the language of the subject matter expert. So these become, that's a car design, it's a car requirement. And you basically, even though formally, all the math is the same, it's all formally the same, but because you're working on categories and categories, you have the opportunity to shift the terminology over to something that is more engineering friendly. And this technique, I call it categories of categories, but no one else does. What you see, for example, in UML SysML, you see what's called meta classes. It's part of meta modeling. This is the construction of all that terminology.
Okay, so it's not even clear. So in your term, categories are meta classes.
Right.
Or another word for that.
Right. Meta classes is actually more general than categories, because you can have a meta class called comment, which is, and comments themselves are categories. So this is sort of loose. Meta classes are the general term. Categories of categories would be a particular kind of meta class. In the UML community, they don't say subject specific, they say domain specific. Domain specific languages. You don't see this mentioned much in the OWL community, which I think holds them back a lot, because although they do partially support this with the construction they have there, but it's just not part of that community to think of categorizing the categories, because that drives the reasoning crazy, and they're very reasoning focused. But they do have a technique to separate the reasoning at the meta level from the lower level so that they can put these things together. It's just not part of their general thinking.
Is that because the whole community is primarily dominated by software people?
Well, no, it's because it's dominated by logicians who, the OWL community became much more rigorous, and it is now, it's better, it's much more scientific, much more rigorous, but they have a bias where anything that causes problems with reasoning is inherently verboten. So this categories of categories is the classic problem in logic that when you make classes of classes, you have a problem. But they actually do have some techniques to separate, because what happens is when you have classes of classes, the reasoners start to get into circle cycles. I couldn't explain it in more detail. But what they do is, with this particular construction, they can separate out the reasoning between the meta classes and their instances and the classes and their instances. Now, keep those separate, and the reasoner doesn't end up going in circles. But they just don't seem to have the motivation because they're so focused on the reasoning. They really focus on only two levels at the same time. So you don't see a lot of discussion of domain-specific languages in the OWL community, which I think holds them back a lot in terms of the adoption. So moving on to relations, I mentioned that categories, the logical modeling includes categorizing the things, but you also want to relate them together. So, for example, cars have engines. You want to know which cars have which engines. Right? My car doesn't have your engine. So what you do is you take the two categories that you're relating, and you make what I'll call these links that connect the individual things. So my car is connected to the engine in that car. And so what you're seeing here is we talk about taking those individual links and making that category. What I have here is a category of car engine links that tells you for every car which engine is in it. And this, again, the terminology, which is sometimes confusing. In UML and SysML and OWL, these are called properties. We'll say the car's category has a property which tells you which engine is in it. They're also called associations in UML. And the things that fall into these categories, the nomenclature really gets broken up here, but I call them links, which only apply to associations. But this whole area of UML needs to be rationalized. If you think of it that way, that's the way to start. So the graphical notation, when you see this in SysML or UML, I've omitted the block stereotype, but it more or less looks the same. You'll see a property written like this or like this. And this is called association. And the end is called property. So this would link the category of cars to category of engines, or associate those categories, and the instances are the links between each individual car and each individual engine. So once you have that, you can start doing generalizations as we did before. Because we know, for example, the relationship between cars and engines is a special case of physical containment, because the engine is wholly within the boundary of the car. Well, there's lots of physical containment links, of course, but the car-engine links are all physical containment links. And if you remember generalization, you see we've applied generalization to relations here. A simpler example is, the relationship to your sister is also a sibling relationship. It's just anyone that's your sister is also a sibling in that relationship, and it forms a generalization. And that, again, going back to terminology, in UML it's called property subsetting or association generalization, and UML is called subproperties. So here's a notation for it. If you see it sometimes if you see it in UML or SysML, you'll see here's the property physically contained on physical things that relates physical things to themselves. Which doesn't mean that things contain themselves, by the way. This is the problem with calling that, if I were to call that physical thing, a lot of people are confused by this because it looks like I'm saying a physical thing contains itself. This is just a category. Now down in cars, I say that specifically this has engine property is, quote, subsetted from the physically contained property. And that just means anytime a car has an engine, it is also physically contained. And this allows reasoners that would say it purely physical at a higher level. Say you could have reasoners that work at a very general level of containment. They don't care what kind of containment it is, they can still do all their reasoning up here. And then reasoners that really care about the engine can reason at the one particular level. This notation over here is a case where you take this property, you make the association, as in the previous slide, with the property. And what you can do in UML and SysML is you can make another class or block that corresponds to that. this is the category, it's instances of the links. And you're just saying the has engine links are all physical contains links. Where this one is what's called the association class for that association. And this is pretty important because when you break up these large taxonomies of things, you usually have to have an equally large taxonomy of relations, which a lot of people forget about and ends up being buried in the code or someplace else or in people's heads. It's better if you can break it out and actually say what you mean in the area of relations. So again, because there's just one slide on it, but you can use the fact that you have relation categories to do subject-specific languages. For example, before, remember we said that this was essentially saying that, this is no longer the plural, sorry. The car design, every car that meets this design also meets the requirements. This is your ideal. Now in SysML, you see this notation, which is more engineering friendly. It says that this car design satisfies that requirement. That's what the engineer wants to see. Even though it's semantically the same as this. So the way you model that is you say, okay, we'll have categories, have relation categories. Particular kind of link at the category level is generalization. That's this one. And a particular kind of generalization is satisfaction, requirement satisfaction. So this is how you build up the relation side of your domain-specific language. I just listed these. I'm not going to go through them. There's other logical constructs you can learn about in ML and UML. These down here have to do with how you hook things together into composite wholes. Like you have to take the engine and the wheel in a particular car and hook them together and that sort of thing. So that's another area of UML and SysML. And just, I thought I would do one slide on how this applies to processes. This could be another topic. But, whenever you want to apply categories, you have to ask, okay, what falls into the category? That would be your first question. Well, if I want to apply categories to processes, what are the things that fall in the category? Well, one approach to this that we took in this was to say, okay, well, the things that fall into these, if I treat these as categories, the things that fall into them are the occurrences of it. So for example, say you have a process for commuting. Well, you commuted today, that was an occurrence. You commuted maybe yesterday, that's another occurrence. They're all separate occurrences. They start at certain times, they end at certain times. They have to fulfill certain conditions to be commuting. So basically you say, okay, well, this is a process written in a little flowchart language. This could be UML or Ethernet. What are the conditions that this occurrence is going to fall into that category? Well, you have to have the paint happen, and it has to be complete and then dry, and you can see that's the case here. We have a painted and then dry, so it's satisfying the conditions, falls into that. And then you can use generalization. Here's a case where I've said, okay, well, I'm making some process. It also paints and dries, but it does some other things. In particular, it spray paints, it doesn't just generally paint. It also cleans up afterwards. So you see that falls into both of them because it in fact does paint and dry just according to these conditions, but it does them more specifically by spray painting and also does a cleanup afterwards.
You can model those in state chart
You could. This could be a state chart.
most of the time.
It depends on your domain. System engineers often draw these things, and for the business process modelers, many engineers also use state charts. All of those things would be models that you can take to be categories of their occurrences. And then, of course, we know from generalization that every occurrence of this, every instance of this, has to be an instance of that. So that means there are no occurrences that only fall into this category, at least there should be. Anything?
But this diagram you have there on behavior, it is explicit about time. It doesn't have one just next type.
Oh, you mean this one?
Yeah.
Yeah, these are the occurrences just telling you like a timeline when they occurred.
This is time explicitly. It's not just like what I do in automata, where it says next state is that. It says
Yes.
how long I stated.
Yes, what I was intending to draw here, these are the instances that fall into the categories. They have specific start times, specific end times. they wouldn't be normally called a process or behavior model because there's only one. Whereas this is a model, quote, model or category of many occurrences. All that's required is that they meet these conditions. And this is the inside when you're applying categories to processes, is that these little arrows in the temporal, those are just temporal constraints, they're just conditions. So you can actually apply logical modeling to processes.
But if I go back a little bit, okay, and I start building things up, if I'm trying to build a process model by starting to find sequence diagrams and then, activity diagrams as special cases of these, then there will be exclusive time.
You can in an activity diagram say, for example, that paint should take no longer than a certain amount of time.
Right. Because that's what I'm getting at. I need to be able to annotate my behavior diagrams with requirements that they have to do with
Have to do with time.
Right.
Absolutely. Right. The thing you typically want to do is constrain this so much that you meant that particular occurrence.
Right.
Because then it wouldn't be a useful model.
Right.
But you do have constraints on time up here. But in fact, this graphical notation is just made graphical simply because the temporal constraint of one occurrence ending before another starting is so common that it's turned into this particular graphical notation.
And then I can link this, right, because the paint box you have there can be a category, and you have several subcategories. One of them may be spray paint, but I have other paints.
Right, you can have a whole taxonomy of paint.
Right. This is what, in manufacturing, for instance, we call process model, manufacturing process model. It can be like a very big graph or a tree that shows how the various processes, some processes connect to each other, and how they have attributes which are related to time, quality, and other things.
Yes.
That's what we care in engineering. So that's the next way. Try to ask the question, I'm going to make this wheel of a car. Which process I'm going to use to make it because I have some requirements satisfied. You can start arguing about this stuff.
Right, absolutely.
Okay.
So that's
And then you can hook this together, right? You can have several processes and then you can hook them together.
right. What you're seeing here is actually, say, the definition of spray paint is actually in another model somewhere else. What I've done here is reused it.
Put three of them together.
Yeah. So these are actually a different kind of thing, which I loosely call a usage.
Right.
The definition of those things is actually elsewhere. And of course, there's a set of terminology around that in various languages. So what you're seeing here is, you're essentially saying that the first thing that happens, or what has to happen here, is an occurrence that meets the conditions that you get when you look at the definition of spray paint. Which, as you said, it's in a taxonomy in such a way that it will also meet the conditions of paint.
Are we in a position now to basically, when I have a graphical tool and I want to create a project model, I can basically go open up a library like we do for network, for instance, and pick up boxes and start putting them together, and the software automatically tells me whether this is a legitimate sequence of process or not. Do that stuff like that?
Well, and you can definitely do the first part, the modeling part. The checking part is dependent on the tool and the quality of it.
These are typically intended to be domain specific checking.
Yeah, like the business process tools are all very good.
Okay. Because every time I do anything like that in manufacturing, and that's one of my frustrations, we have to start from scratch.
Oh,
That's not across.
Oh.
So whether I am microelectronic manufacturing or car manufacturing, at least I don't know the system where it is allowed to go across.
Go across in the sense that they have
The process.
they have model libraries and you
Yeah.
both of the tools.
The process is specific, not the part. The
Process, yeah. That's a good thing to look into that. So, I'm getting close to the end here. So by now, you understand logical modeling is all about categories, loosely speaking. You have to learn the terminology of particular languages, but that's the word I use. We learned that these categories are really the conditions for things to fall in them. They're not the things that fall in them, they're not the set of things that fall in them. We learned about the various kinds of conditions, and the most common one being generalization. And then we saw that relations we treat as categories of the links between individual things. You can form categories for the domains that are subject to the languages. And probably, as I mentioned, quite important is the fact that these ideas aren't so hard to understand themselves. It's actually the real work is mapping them to various languages that are out there and getting used to doing. And we saw some applications for the product and process modeling. So if you want some references, UML is here. These are actually easy to find now. This 1.3 of UML, of SysML, which actually has a big upgrade for modular systems. That link is not accessible outside of the LNG. If you wanted, just I put my email spelled out here. Just send me an email.
Which one's on the available?
This one, you have to be an ONG member to get that link, but I'm glad to send it to you. I'll point you to where you can get it. This is a pretty important upgrade because it deprecated a couple of things in this one. This is OWL. Actually, they have a very nice overview and examples. They have many different textual notations you can use for OWL. You don't need to write an XML if you want to use it. These are a couple of papers you could look at for the application of these ideas of product modeling and behavior modeling. There's also other material. If you just actually, I have another website I can send you. If you just send me an email, there's other material presentations.
Thank you very much. Questions?
So I'm trying to understand how you extend this to behavioral modeling.
Oh. That had to do with, I really only gave one slide on it, just to give you an idea, because we're running out of time. When you think about the categories, you apply it to behavior or process. Behavior is actually UML SysML word for process. So when I say behavior modeling, it's just UML process modeling. And when you make a category, the concern for what you can put in the category, and with regard to behaviors and processes, what you put in is a single occurrences of it. You can do today, you can do tomorrow, separate occurrences, and that's what those timelines are. They're meant to be, I started the change color process at this time, I ended it at this time, and it's a single occurrence. And that's beating the conditions here, because within that occurrence, I did a paint, I did a brush paint, it's dry, and that counts, that follows these conditions. So you follow that through, and you can make taxonomy where the occurrences that say meet these conditions also meet the ones that are more general.
The times are the soundtrack. You see that?
Yes.
If I add the times, the ones that before. It says color times as well, but the component process has smaller times when you put them together. You have that.
Yeah, there is of course a lot more to this because you have to relate, say, this change of color occurrence to the dry occurrence that's in it, not some other dry occurrence. So there's of course a lot. This would be another talk, but I wanted to give an example. And it's not categorization. It's not just about physical things. It can be about processes.
It seems like there's kind of, ever increasing levels of detail that you could impose, because, for example, some drawing processes would or would not be compatible with some painting processes, and those things have to be meshed up at some level.
Right. Yeah. Hopefully the analyzers and reasons help you tell when you essentially created. What the reasons do is they help you say you define this. It's got all these conditions in it. Well, it turns out that even from a theoretical perspective, there can never be an occurrence because there's some contradictions in the painting and the drawing conditions. And that's what the analyzers and reasons is what help with.
So you can do that easily by things like constraint-based reasoning, or if you want to do more, you can reduce the particular constraint-based reasoning, like satisfiability problem, or even if you want to do more sophistication, as we heard from in briefing, or actually you can use some material provers to tell you because of some of the things you want are true or not. You can be very sophisticated. Any other questions? I have two questions, right? The one is, don't take it back, but I have to ask you, because the students ask me to teach this stuff, and it seems to be that what some of the best students are telling me from many universities and to others is that we keep increasing the notation and the semantics of all that. And the
fan out is actually growing to the point where people are asking the question, how am I going to learn all that?
You mean all the notation?
Yeah, can we find some shortcut so we can actually teach it in a semester or two,
Mhm.
and the people start doing things? Because, especially in engineering, people are now beyond the, trust me, this is good, and one time you will actually use it. They want to be able to go immediately and start using it.
Mhm.
And we saw this both in the undergraduate and the graduate courses, and we have students here, you can comment on all that. I've heard this loud and clear.
Mhm.
Any predictions of where we're going to go to something that is more learning friendly and using friendly, let's
Yeah.
put it that way?
Yeah, the unfortunate thing about the standards groups, at least at OMG, is that they're user focused, but they're mainly for vendors to be able to implement stuff. Now, what they don't have is standards for how you teach it or how you break it up. And often
This is for us.
the standards, in fact, yeah, I pointed at those standards, but I actually wouldn't recommend you read them. They're actually for people who are involved in it, and the vendors all understand it. And then there's it actually spawns this whole industry of what are called methodologists that teach it. But the trouble is, OMG doesn't currently have a way to regularize that. And it would be very useful. Well, Sandy's book is great, but it's also comprehensive. I mean, there's a lot of material. Okay, which sections, which chapters do I have to read to do which thing?
And my limit for a book is 150 pages per class. After that, I start getting violent rewards from students. Too long. Because basically, it's this model that you want to have, which is based on lectures, right? So I have X number of lectures,
Yeah.
and I want to have about 8 to 10 pages per lecture that's doable in the lecture. So it's always, right, a very difficult selection problem. Which ones I select with the basics, and I let the other people read it. And I guess the subject is too young to have that level of development.
Maybe it's something amiss and we're only coordinate on and developing sort of syllabus for that.
Or even try to do some electronic version of this in the beginning.
Yeah.
Because then you can change it easier, right, based on feedback.
That'd be great, yeah.
Yeah, that's something I'm interested in. The other one is more technical. Okay? So we worked with a group, both in Europe and here in the US, that have developed a methodology, which is not new. It's old, but this version is better, which is called contract-based design, right? What contract-based design is, in very plain language, is I basically take several specifications that you give me, and I express the relationship between the blocks and the requirements and so forth as quote-unquote a contract, which is a word of saying you have to satisfy these things before you go any further, and that there's a way to compose this and so on and so forth. Any comments on whether this has reached OMG or the circle you work with?
Well, I guess it depends on exactly what's part of the contract approach you're taking. But this 1.3, which was a long time coming out, was a long discussion about modularity, how to define the interfaces and so on. And so there's been a lot of progress going to 1.3, and actually it's been simplified with some interest, because some constructs were deprecated and others pushed together. So we think we're farther along on a simpler specification for modularity.
Any other questions? Right.
What kinds of industries are you interacting with? So it seems like you're already thinking about training and training practicing engineers. What kinds of industries are you interacting with?
Everything.
They tend to be, well, there's a lot of aerospace because, well, since I'm more involved with SysML than you know now, but there's a lot of aerospace because that's where it started. But then Deere has always been present, and NASA is involved now a lot.
The government uses a lot of SysML. That's why industry is moving towards SysML.
But the aerospace is using it independent from the government, because what Boeing and Dassault and Aerospatiale do that, and then the government has to do the fact that the complexity of the system is such, and the supply chain is so complex. If you don't do that, forget about being able to have 800 manufacturers, so when they give you the pieces, you can check them, put them together, like you said. Okay. The encouraging thing is microelectronics. And if you come next semester, there's a talk exactly for you from one of the experts on using this for mixed system design, analog design. Yeah, it's interesting that some of the microelectronic people are moving in this direction.
It's where the layers of it are such that any one contracting with the DoD ends up doing something like this, because it's UML, SysML, and then the profiles that capture DODAF, the DoD architecture framework. So it's, a lot of it is driven out from DoD to the various contractors. That's happening quite a lot.
And nationally, both nationally here and in Europe, although this particular twist is more from here, is they're trying to go to the situation, not now, but maybe in a few years, where various pieces are described as models, which are not, they describe a wheel as a model, but they allow you a lot of freedom to choose which wheel and design it. So that the idea is you could have these pieces out there as models in software. You can take them, make the system, and then go to manufacturers and say, you know, you bid for that piece, you bid for this piece, you bid for this piece, and when you come in, I can check it, and when I put it in, I have a certified safe assembly, which can be done for microelectronics and for mixed microelectronics, and can be done for MEMS even, but not in a very well integrated set. And definitely can be done for cars. What the car industry has done in this area is way ahead of everybody else. Some, I should say, an expert here, we've seen it firsthand, is that some car industry, not all, but they really won't move that way. Again, because of this business of manufacturing and that you're not going to get another team like even Apple under Steve Jobs, right? They had this inner team that was essentially integrating and thinking of everything, but then they had to deal with 800 vendors. Now they didn't use these tools, but they used other things that they had in that regard, which they safeguarded very much at that point.
So are you moving in the direction where platform-based design would be like a standard?
I don't call it platform-based design, forgive me for not adopting the very late terminology. I call it system-level design because platform-based design has certain connotations that I'm not happy with. Right? Because platform-based design means I have a basket of pieces and I combine them to make a thing. Right? And I want to allow for the possibility that you may ask the question, is there a piece that's missing from my basket that I need to create that kind of system? Give me the specs for it so I can go out in the market and see if anybody can build it. So I want to be able to get out of the platform if I can.
The next revision of SysML, the plan is for it to address what's called variant design, which is blended platform. That is, you have something in common between all these products, but they have variations. And you can do this in SysML now. It's just cumbersome, and it's a high priority for that group to have some upgrades to simplify the development of variant models.
So you will have platform-based design as one philosophy, but you will also have components and architectures and system-level design that they're not exactly the same. Okay, because the key question that is being debated right now, and people are trying to define it by themselves, is what do you mean by an architecture? So there are at least 5 definitions I can give you, and you can argue which one is. System architecture is a big question. What is the system architecture and how it's emerging from all these considerations? And there's even a question of whether you need architecture specific languages, right? As the domain is architecture, you won't have an architecture language to define the architecture. Platform-based design is one thing that you need to consider, but it's not everything. To answer your question. Right. Thank you very much.
Thank you.